Okay, and we're in section 8.1, and we're talking about the sampling distribution of the means. Okay, the idea here is if we were to take several different samples of a certain size and calculate the mean each time, like what would that look like? What would those means look like? The two properties that we had left off within the previous video said that the mean of all the sample means is the same as the population mean, and the standard error is found by taking the standard deviation divided by the square root of the sample size. Okay, these are the two things that you should know for this section. Okay, mu sub x bar is the same as mu, and sigma sub x bar, that's the standard error, is found by taking sigma divided by the square root of n. I want to go through a demonstration of these two properties just so you can kind of have an idea of where these formulas are coming from. So let's take a look at that now. It says that a doctor randomly selects 45 of his patients and obtains the following data regarding their serum sodium levels. And for the purpose of this demonstration, we're going to consider the group here as our population. Okay, so suppose that this is all 45 of the patients that this doctor has. Okay, and here's their serum sodium levels. A histogram for the data is shown below. Okay, and I used a program called StatCrunch to be able to draw the histogram that you see here. And that allowed me to overlay the normal distribution curve on the histogram. And so we can see that the shape of the data set is normal, or at least approximately normal. Okay. Notice how the shape of the graph is approximately normal. And it also allowed me to calculate the population mean and the population standard deviation. Okay. So the mean of these 45 serum sodium levels is roughly about 139.6, and the standard deviation of these 45 serum sodium levels is roughly about 5.53. Okay? Using StatCrunch again, I was able to obtain 20 random samples from our data set, each of size n equal 5. So here's the original data set. I took 5 numbers and calculated the mean and put those numbers back, and then I selected 5 more numbers, calculated the mean, put those numbers back. I selected 5 more. It was a random thing. Okay, or I had StatCrunch do this. Okay, and so suppose that I did that 20 times. Okay, I had StatCrunch do this 20 times. The first 4 of the 20 samples are shown below. Okay, so here's the first 5 numbers that I selected from the 45, and I found the mean of those 5 numbers. Here would be the second group of 5 randomly selected and the mean of those 5 numbers, etc. If we go to the next page here, the complete set of the sample means is shown below. Okay, so I mentioned that here's the first 4. So here's 134.8, 138.6. Okay, here's all 20 means that are shown from what StatCrunch provided me. Okay, now with these 20 means, I took the numbers and I created a histogram using StatCrunch. Here's that histogram. And it also allowed me to overlay the normal distribution curve, so we can see that the shape of this graph, these 20 means, is approximately normal. I was also able to calculate the mean of the 20 means and the standard deviation of the 20 means. The mean of the 20 means is about 139.2. And the standard deviation of these 20 means is about 3.07. Okay, now it says in problem 2 here, how do these two histograms compare? Specifically, compare the shapes, the means, and the standard deviations. Okay, so Here was the histogram for when we had the, from the original data set using all 45 numbers. Here is the histogram using the 20 means that I've created. Okay, how do these compare? Well, they're both approximately normal. I mean, we can see that from the normal curve that's been overlaid on the histogram. And they seem to have approximately the same means. Like in the original data set, the mean was 139.6 right here. And in the histogram for the 20 means, the mean of those 20 means was 139.2. Okay, so 139.2 is very close to 139.6. The standard deviation of the second one here seems smaller. Okay, the standard deviation of the 20 means is 3.07. The standard deviation of the 45 numbers in the original data set is 5.53, roughly. Okay, so that number is smaller in the second graph, which is going to show less dispersion. Okay, so there's going to be less of a spread in the 20 means than there are in the original 45 numbers that were in the data set. Okay. Using StatCrunch again, I was able to obtain 20 random samples from the data set, each of size n equal 10. Okay, so I took 10 numbers from the 45, calculated the mean, put those numbers back. I selected 10 more numbers from the 45, calculated the mean, put those numbers back. So suppose that I did that 20 times, right? I had StatCrunch do that 20 times. The first 4 of the 20 samples are shown. Okay, so here's the 10 numbers from the 45 randomly selected and the mean of those 10 numbers. I put those numbers back. Here's 10 more numbers randomly selected from the 45. I calculated the mean, put those numbers back, etc. Okay. On the next page, here's the complete set of the sample means for when the sample size was 10. Okay, and you can see that the first couple of numbers here are the same. Here's 138.6 and the 138.9, etc. Okay, so here's all 20 of those means for when the sample size is 10. Using these 20 means, I then used StatCrunch to be able to draw a histogram again. That allowed me to overlay the normal curve. We can see that this is approximately normal. Okay, it also allowed me to calculate the mean and the standard deviation. So the mean of these 20 numbers here, these 20 means, is roughly about 140.2. The standard deviation of the 20 means is roughly about 1.67. Okay. Problem 3, compare the histogram with the previous two. Specifically, compare their shapes, means, and standard deviations. Okay, well, all 3 of these histograms are approximately normal. Okay, so the distribution remains normal, and the mean seems to be approximately the same for all 3. Okay, the mean of these 20 means here, when the sample size was 10, is 140.2. The mean of the 20 means when the sample size was 5 was 139.2, and the mean of the 45 numbers in the original data set is 139.6. Okay, so all 3 of those numbers are pretty close to each other. Okay, it's approximately the same for all 3. The standard deviation gets smaller when the sample size gets larger. Okay, the standard deviation for the 20 means when the sample size was 10 is 1.67. When we had this samples of size n equal 5, the standard deviation was 3.07. The standard deviation in the original data set was 5.53, roughly. Okay, so you can see that the standard deviation is getting smaller when the sample size n is getting larger. Now, I think that should make sense to us. If you're working with a bigger sample size and you have something that is normally distributed, well, the majority of the data is going to be around the mean, right? That's how we're getting the bump in the graph. So if I'm randomly selecting more numbers, like they're probably going to be numbers around the mean. Okay, so there's going to be less of a spread than in the means for when you're increasing the sample size. In general, that's going to happen. Okay. Problem 4, do the properties of the distribution of the sample means seem to hold true for the previous demonstration? Okay, so these two properties on the first page are the things that you need to know. It said the mean of the sample means is the same as the population mean. Well, I think I buy that here because, you know, all three means were roughly about the same. We just mentioned that here, okay. For n equal 10, the mean was about 140.2, which is about the same as the original. It was 139.6, okay. So yeah, I think I buy the first property there. Now, the second property, talking about the standard error, so the standard deviation of the sample means is found by taking the standard deviation divided by the square root of the sample size. So let's see here. The standard deviation when n is 10 is about 1.67. Okay, and that's again coming from StatCrunch here when n is 10. Now, using the formula that I just showed you here, if you were to take sigma, which was there for the first graph, 5.53, and divide by let's see here, so 5 I use more digits, but take 5.53 and then divide by the square root of n is 10, you would get a roughly about 1.75. Okay, so I think I buy that the properties hold true because these numbers are pretty close to each other, you could say. Now, when you look at these formulas, notice how there is no approximation sign. Okay, like I'm using an equal sign. The mean of the sample means is equal to the population mean. The standard deviation of the sample means is equal to the population standard deviation divided by the square root of the sample size. So why does it look like these are a little off? Well, it's going to be a little off since we did not find all the possible samples of size n equal 10. You see, we only used 20. If we had used all of the possible samples of size n equal 10, which, by the way, if you were to look at all the samples of size n equal 10 from 45 numbers, there would be over 3 billion of them. Okay, so we've only looked at 20 out of more than 3 billion. Okay, if we had looked at all the possible samples, I've got that underlined, if we had looked at all the possible samples of size n equal 10, then the formulas would be exactly equal as it's stated. Okay, but you can already see that just by looking at 20 numbers, 20 means here, we are pretty close in you know, the actual values there. Okay, so in this demonstration, I just kind of want to have you guys see where these two properties are coming from. Okay, in the next video, I'll work through a couple of examples using these properties.